Hello all, welcome to our critical design review presentation. Our project is TEXRAY, textile identification via Raman spectroscopy.
This is our team. I'm Ariana Mihendust, Photonic Science and Engineering.
I'm Danielle Samuels, Photonic Science and Engineering.
I'm Austin Frost. I'm a computer engineer.
And I'm Cameron Ricketts, electrical engineering.
Our team was motivated to pursue this project in an attempt to give a little bit of power back to consumers. More and more consumers are ditching synthetic fabrics in favor of natural fibers and textiles for a variety of reasons. Some do so to practice ethical consumption and minimize environmental impact, while others feel that natural fibers are simply more comfortable and will last longer even if they're more expensive. Alongside this changing consumer attitude, however, is an increase in opportunity for merchants to lie about fabric composition to cash in on market trends. Retailers will claim to sell 100% cotton when actually using a fabric blend. Similarly, luxury knockoffs are sold that look nearly identical to the genuine articles but are made of cheaper materials, fooling customers. Consumers have a right to receive the product they paid for as advertised, down to even a single fiber. However, our team noticed there is no easy and affordable way for the average shopper to verify the textile composition of their items. The cheapest commercial products that serve this function are $2,500, which is a hefty investment. This motivated us to find a cheaper solution to serve the market.
Raman spectroscopy is a powerful non-destructive analytical technique used to identify molecules based on how they vibrate, whether that's through rotating, stretching, or bending. For instance, when a green laser is incident upon a sample, most of the light that's scattered is of the same energy, and you'll see the surrounding area look green. However, about 1 in a million of those photons experience the shift in energy levels as a result of the laser's interaction with the molecule's vibrational modes. Raman spectroscopy can measure this energy shift and reveal a molecule's chemical fingerprint. Therefore, we can differentiate textile types by their varying molecular structures.
Our main goal is to classify cotton and polyester samples based on their spectral signature. The samples under consideration are ISO standardized and will be undyed and unblended. We'd further like to implement a second functionality which will be able to conduct a product comparison by their spectral signatures. To achieve these goals, we have been focusing on the objective to develop a robust, accurate spectrometer design paired with user interfacing.
The following are our core objectives to achieve the project goals, which are implementing a methodical optical design to build in effective backscattering light collection and spectrometer configuration, and also the use of accurate comparison algorithms to discern the spectral signatures of cotton and polyester. And to complete all of this while maintaining reliable and portable power supply. This hardware block diagram depicts the general flow of our system design. The top two segments of the diagram detail the optical layout, and the bottom segment displays the layout of the electronic and software components.
For our optical layout, the laser source is directed at the dichroic mirror, which will selectively reflect the laser line into a focusing lens that focuses the beam into a 10 to 20 micrometer spot on the sample. This generates Raman shifted photons in all directions, which are then collimated by the same lens and directed back towards the dichroic. The dichroic will transmit the Raman shifted photons while reflecting nearly all other wavelengths, upon which a long pass filter will fully isolate the Raman signal. This signal is then focused onto a multimode fiber by a coupling lens and is carried to the spectrometer optics. The entrance slit determines how much light will enter the spectrometer and acts as a spatial filter. The diverging light through the slit will be collimated by a plano-convex lens. This collimated beam will then be incident upon a reflective diffraction grating. The light reflected off of the grating will be the Raman signal separated into its respective wavelength components. These separated wavelengths will then be focused by another plano-convex lens onto the CCD array.
This chart details all of our important engineering requirements. The highlighted portion specifies the demonstratable parameters for our final demo. The system should be able to identify a textile sample and conduct a textile product comparison with 90% accuracy. The user should also receive a result readout within 15 seconds of initiating analysis.
At the start of Senior Design 1, we tested various fabrics using a Raman microscope at UCF's Nanoscience Technology Center and found 532 nanometer and 473 nanometer laser light most compatible with our fabrics. Since 473 nanometer lasers are rare and costly, and the more available 450 nanometer options risk increased fluorescence, we chose 532 nanometers as our laser wavelength. Of our options, the The Q BiHa laser module eliminated the need for a separate collimating lens and had a spectral line width under 1 nanometer, supporting high spectral resolution and making it the most suitable choice for our system. In our design, the excitation laser is directed towards a beam splitter that separates the excitation and collection paths in our system. A 50-50 beam splitter would lose 50% of the laser power both before reaching the sample and during signal collection, weakening overall signal generation and collection. Alternatively, a dichroic mirror can selectively reflect nearly all laser light onto the sample and allow Raman-scattered photons to transmit through with minimal loss. It also serves as a preliminary, less effective long-pass filter by blocking most of the laser line from reaching the spectrometer. These advantages made the dichroic mirror the optimal choice for our system. We considered multiple potential dichroic mirrors for our project. Ideally, our dichroic mirror should have a cut-on wavelength near 532 nanometers to minimize Raman signal loss. It should have high transmission at wavelengths above 532, enabling as much Raman signal as possible to be recovered. A large diameter would also contribute to increased signal acquisition. The filter best suited to our needs was the Chroma RT532 RDC, but the cost of this filter was too steep for our budget. Instead, we decided to use the Chroma T550 LPXR. This filter's higher cut-on limits our spectral range to 800 wave numbers on the lower end, but it also has a large diameter and 97% transmittance at 556 nanometers, allowing for high Raman signal collection. The purpose of the filter in our setup is to fully eliminate remnants of the laser line and Rayleigh scattering that were not already reflected by the dichroic mirror and to fully isolate the Raman signal. For our filter technology, we decided to use a long-pass filter rather than a notch filter due to the Raman scattering below 532 nanometers being negligible. The filter we chose is the Chroma ET542LP. Of the prospective long-pass filters, this filter did not have the closest cut-on to our laser line. However, when comparing this filter to those with transmission bands closer to 532 nanometers, we found that opting for the more expensive filter would give diminishing returns in performance and would not be worth the extra money. The high transmission of this filter and the passband that closely aligns with our dichroic mirror makes the Chroma ET542LP the most cost-effective selection.
Between holographic and world reflection diffraction gratings, we found that world gratings were more suited for our application because of their higher diffraction efficiency. A 1200 line per millimeter groove density grating was chosen because higher groove densities result in higher angular dispersion and therefore better resolution in distinguishing closely spaced wavelengths. This comes at the cost of a lower dispersed spectral range, but since we're only interested in a 90 nanometer spectral range, this trade-off is acceptable. The resolving power is proportional to the number of illuminated grooves. Therefore, using a larger grating increases the number of grooves contributing to diffraction, improving resolution. A full illuminated grating can resolve wavelengths less than 0.02 nanometers apart. While the actual system's resolution will be limited by other factors, this confirms that the selected GR25-1205 grating meets our resolution requirements. In comparing two feasible detectors for our system, CMOSs and linear array CCDs, CCDs display higher quantum efficiencies in our spectral region of interest and are more suited for high sensitivity applications, which is critical for receiving the low intensity Raman signals. We selected the Toshiba TCD1304DG, a widely adopted linear array CCD for spectroscopy, due to its 29.1 mm detector width to capture our full 90 nanometer spectral range, its 8 micrometer pixel width, offering a sufficient resolution given our 25 micrometer slit, and a spectral sensitivity aligned with our region of interest. The detector's dynamic range of 301 enables us to differentiate signals with significantly varying intensities. With a clock frequency of 2 MHz to drive the CCD, the output is captured at a rate of 500 kHz. This quick data rate helps minimize our system's total response time. Since we're dealing with low-intensity signals, we may need to increase the integration time to improve the signal-to-noise ratio. However, we must be mindful of the resulting accumulation of noise. The spectrometer portion of TEXRAY is responsible for separating our Raman scattered light from the illumination optics into its constituent wavelength components. Our desired spectral range is 550 to 640 nanometers, which corresponds to the range of shifted wavelengths that contain identifying peaks for cotton and polyester. We're looking to achieve a spectral resolution of less than or equal to 1 nanometer to thoroughly differentiate cotton and polyester spectrum, as well as conduct a reliable product comparison. The final component on the illumination optic side is a 75mm focal length condenser lens that will focus an 18mm beam onto the slit. This results in an F number of 4.16. In the spectrometer design, I carefully matched this F number through my choices of lens diameters and focal lengths to increase the light throughput of the system. To satisfy the Nyquist sampling requirement for discerning a wavelength peak, the 25 micrometer slit image should span at least 2 to 3 8 micrometer pixels. A 25 micrometer slit paired with a 50 millimeter focal length collimating lens results in an approximate 0.4 nanometer resolution. The 29.1 millimeter wide detector paired with a 50 millimeter focusing lens allows for a receivable wavelength span of over 400 nanometers. While some of this wavelength span will be limited by optical and detector capabilities, our desired 90 nanometer span is fully captured. A symmetrical spectrometer layout where the collimating and focusing lenses have matching 50 millimeter focal lengths provides a compact configuration that still upholds our desired spectral range and resolution targets. This is the ZMAX simulation of the spectrometer design. ZMAX was used to dictate our lens choices and showed acceptable spectrometer performance with a 50 millimeter focal length achromatic doublet for collimating and focusing. I was further able to optimize the distances between lenses that derive tolerable spots. We could also see that the distance between 550 and 640 nanometer wavelengths on the focal plane is 6.419 millimeters, which will fit comfortably onto the 29.1 millimeter detector.
Moving on to the electronics portion of our project, while each power source option had its own distinct advantages, the DC battery was chosen due to its reliability, cost efficiency, and portability it gives to the Raman spectrometer system. As far as the type of battery implemented, a lithium iron phosphate battery was selected in order to ensure a safe and stable output with high capacity and long lifespan. More specifically, a rechargeable battery pack was selected for simple integration. This schematic is for the 12-volt regulator, which is specifically assigned to supply the laser with the voltage needed for operation. In this regulator schematic, the output voltage will be 5 volts and will be used to power the Raspberry Pi and the microservo, which will be the blocking mechanism for the laser. The last regulator schematic is a 3.3 volts regulator, whose main priority is supplying the ESP32 and the CCD sensor. This schematic outlines the connections being made on the main board between the components. The regulators are located at the bottom. The ESP32 can be seen in the middle, which is connected to the CCD on the right. The CCD will transmit the collected data to the ESP32, which will also communicate with the Raspberry Pi. On top of the Raspberry Pi, there will be a LCD externally connected directly to it. The CP2102 is located at the top and will be used to program the MCU. Here we have the PCB layouts for all the regulators. They will ultimately be through-hole soldered onto the main board for operation. Here's a layout of the main PCB. At the very bottom is the input from the battery source, which is followed by a switch to power on the device as a whole. Slightly above are the 3 regulator boards. To the right of the board is a blocking motor device and the laser, which will both be plugged into pin headers. The CCD is in the top right corner and is intentionally placed there so it will be the furthest from the voltage regulators in an attempt to avoid any noise emitted from the switching regulators.
There were many microcontroller options available that met all requirements for the system, but given the slightly lower cost, higher clock frequency limit, and my own previous experience with programming for it, the ESP32 was the most logical choice. There were fewer but still several options for the single-board computer as well, but ultimately the level of community and first-party support available for the Raspberry Pi dwarfed that of comparable devices, and that, along with a more moderate price tag, made it the clear choice. Since the LCD screen in our system will be operated by the Raspberry Pi, the Hazian 5-inch Raspberry Pi display was chosen for this project. There are 3 methods of comparison used in the data analysis phase of the project, all ranging in scale and application. The main method at the core of the project's software is dynamic time warping. This algorithm was developed to more accurately compare different time series, meaning any line graph in which the data points are arranged in order of time. Using this algorithm, the effect of time is limited on the comparison, as points are selected between different series by their similarity rather than their linear place in the series. This is done by determining similar points using distance formulas, irrespective of their place on the x-axis. An example of this would be the analysis of different people walking, comparing them by ignoring the pace of their walks and instead looking at the visual aspects of them walking, how far they move their arms or how wide their strides are. DTW goes through each data point in the first series and finds a comparable point in the other line. These are called points of comparison. D2W's resulting similarity score is the sum of calculated distances at every point of comparison. The method of calculating distance can vary. We're using Euclidean distance, which takes the Cartesian coordinates of both points and measures their distance as the hypotenuse of the right triangle formable between them. The next method is k-nearest neighbors, which is used to determine the final result of material analysis. The algorithm takes a missing point from a data set and sorts it into one of several groups by finding the closest pre-existing data points and sorting the current point into whichever group is most represented among the points in close proximity. The distance metric we selected for k-nearest neighbors is again Euclidean distance. Once the user has their sample in place, their interaction with the system begins by selecting a setting through the LCD screen. The two settings are titled Material Analysis and Product Comparison. Selecting the former will return the identified material of the current sample to the LCD screen, while the latter returns whether or not the current clothing item has already been scanned and stored. In product comparison, if a match for the clothing item is found in prior scans, then the ID label of the match is displayed, whereas if no match is found, then the user is prompted to input an ID label for the new clothing item. The output of the spectrometer is obtained from the CCD sensor. This is done using the ESP32 on the PCB. The CCD sensor has pins for supply voltage, ground, and output, which are all connected to the board, as well as pins for clock, shift, and clear gates that drive the output of the CCD. These three pins receive timed voltage signals using the pulse width modulation channels on the MCU. By setting the frequency and duty cycle of each signal, the output of the CCD is coordinated with the sampling rate by the ESP32. This way, the MCU receives the analog voltage output from the sensor and converts it into an integer array using the controller's embedded analog-to-digital converter. The converted CCD data is then sent from the MCU to the Raspberry Pi for analysis. This transfer is done using SPI. The received data is displayed to the user in the form of a spectral signature graph using the MATLAB Python library PyPlot. This is done after first fitting the data to a calibrated wavelength axis, subtracting the background noise from the dataset, and finally smoothing the results using a Savitsky-Golay function available in the SciPy library. The finalized signature data is then used for comparison against previous signatures through dynamic time warping, and the resulting array of comparison values is analyzed to produce the final result of the system. In the case of product comparison, the DTW results array is searched through to find if any signatures pass a comparison threshold to be identified as a match. And in the case of material analysis, the results array is analyzed with k-nearest neighbors to find which material group the sample is best sorted into. Software used for this project includes the Arduino IDE for programming the ESP32, Visual Studio Code and Google Colab for the Python code testing, and the Raspbian operating system for running the tested Python code through the Raspberry Pi terminal. The Python libraries used are NumPy for manipulating the digital spectrum data, SciPy for the easy-use Euclidean distance function, scikit-learn or sklearn to import the k-nearest neighbors classifier, and PyPlot for the MATLAB plotting library to generate the spectral signature graph.
To assess the feasibility of our optical design, we created a preliminary setup of our collection optics using only lenses and filters available in the Creo undergrad lab. We tested a transmissive Raman configuration with a 100 milliwatt 532 nanometer laser focused onto a liquid ethyl alcohol sample using a 50 millimeter focal length lens. The resulting Raman signal was collected with another 50 millimeter lens, passed through a long-pass filter, and focused onto a spectrometer fiber with a third 50 millimeter lens. Ethyl alcohol is known to have an intense Raman peak near 2900 wave numbers, which we could clearly observe in our results. This assured us that a 10-second integration time should be sufficient to discern a clear Raman signal. Additionally, since the spectrometer we used contains a CCD similar to the one in our design, this test also validated the sensitivity and resolution of our chosen detector.
Software testing at this point has reached completion for CCD data acquisition, as showcased here with the voltage output of the CCD being displayed on the oscilloscope and the ADC's converted integer values displayed with the serial plotter function in Arduino's IDE. These results come from a finger being placed at various points along the sensor, which is visible in an upward spike of each frame, which indicates a darker lighting on that area of the sensor. The sensor's output is controlled by timed voltage signals from the microcontroller, just as it will be in the final project design, with testing using the ESP32 dev board instead of the embedded MCU on the PCB.
This is a note of our progress thus far. We have experienced various difficulties and successes in the implementation of our optics and electronics. On the optics side, we tested and explored many laser sources and ultimately found the one that provided a narrow line width while being centered at 532 nanometers. The spectrometer portion faced an extensive process of simulating various configurations and combinations of optics that would serve our goals. Ultimately, a configuration has been decided upon. We have further been developing mounts for the optics. The TCD 1304 timing requirements has caused delays in the implementation of the CCD data acquisition as discussed in the previous slide. We have also been troubleshooting the PCB and regulator designs. As expected, there were flaws in the original design and appropriate adjustments have been made to alleviate them.
The next phase of developing TEXRAY involves the alignment of our illumination optics and spectrometer, integrating the CCD with the optics, developing the spectral analysis software, implementing the PCB, and designing the housing.
Our system is projected to cost just over $1,500, about $1,000 less than the cheapest comparable textile identification device. This would mean we have succeeded in our goal of reducing the cost of material authentication for the average consumer.
Here we have a table of our team's work distribution for the project.
Thank you to Chroma for generously lending us a dichroic mirror and long-pass filter, and to Test Fabrics Inc. for providing us with industry-standard fabric samples. This has been our project, TEXRAY.